For decades, the Big Bang has stood as the ultimate beginning of everything we know. But now, the James Webb Space Telescope may have detected something that does not fit that story. Something so old, so unexpectedly mature, that it raises a chilling possibility. What if part of the universe is older than the beginning itself? What Webb is seeing in the early cosmos is forcing scientists to ask a question they never wanted to ask. Did the universe begin exactly where we thought it did? Or have we only been looking at the first layer of a much deeper history? If that sounds fascinating, please take a moment to like, subscribe, and share this video. It really helps the channel grow and allows more people to discover these cosmic mysteries. And as always, thank you sincerely for being here and spending this time with the channel. It is always a pleasure to have thoughtful viewers from around the world. If possible, please let us know in the comments what time it is where you're listening from and which part of the world you're in. Now, let us begin this journey into one of the most unsettling discoveries James Webb may have revealed. The correction does not arrive as a dramatic announcement. It begins as a quiet embarrassment inside astronomy, a slow accumulation of details that refuse to stay where they are supposed to stay. For generations, the Milky Way is treated as a familiar object, grand but manageable, a spiral galaxy about 100,000 light-years across, with a bright central bulge, a set of sweeping arms, and a neat place for the solar system in one of the quieter lanes. That number settles into textbooks, lecture halls, museum walls, classroom posters, planetarium films, and public imagination. It becomes less a measurement than a fact of nature, something so often repeated that it starts to feel permanent. But permanence in astronomy is usually just a pause before better instruments arrive. The first sign of trouble is not a single discovery. It is the growing sense that the visible Milky Way and the actual Milky Way are not the same thing. Astronomers already know that living inside a galaxy makes it unusually hard to describe. They do not stand outside it the way they stand outside Andromeda. They do not see its full silhouette against empty darkness. They sit buried within one of its spiral structures, surrounded by dust, gas, bright nearby stars, dark clouds, and crowded lines of sight. In some directions the galaxy looks thick and brilliant. In others it fades into apparent emptiness. The old measurements do not come from carelessness. They come from a practical limit. Earlier maps mostly follow what telescopes can see: clearly bright stars, glowing gas, star-forming regions, and large structures traced in visible light. Where these thin out, astronomers draw an edge. It is a reasonable edge. It is also, as new evidence begins to suggest, a false one. The unsettling part is not simply that the Milky Way might be larger. It is that the galaxy seems to keep continuing past the place where it was supposed to end. Faint stars appear where only sparse outskirts are expected. Thin stellar populations linger at surprising distances. Clouds of hydrogen drift in regions once treated as almost empty. Small satellite galaxies move as though they are orbiting something larger and heavier than the visible galaxy should allow. The motions do not match the map. That is where the calm surface starts to crack. Astronomy trusts motion because motion is harder to fake than brightness. Light can be hidden by dust. It can be dimmed by distance. It can be missed entirely if an object is too faint, too red, too diffuse, or too far. Gravity is less polite. Gravity leaves signatures in speed, orbit, curvature, and pull. If stars at the outskirts are moving too fast to be held by the mass that is visible, then either the measurements of mass are wrong, or the measurements of size are wrong, or the underlying physics is incomplete. For a long time, the usual answer is dark matter, the invisible material inferred from gravitational effects. That answer explains much, but it does not make the discomfort disappear. Dark matter itself raises a new question. If the dark matter halo reaches much farther than the visible disk, then what exactly is meant by the size of the Milky Way? The old number begins to look less like a true diameter and more like the diameter of the bright part alone. And once that distinction enters the story, the older certainty starts to dissolve. The galaxy becomes difficult again. The bright spiral shape familiar from illustrations is no longer the whole structure. It is only the inner expression of a much broader system, a visible island sitting inside a larger gravitational domain. That larger domain does not announce itself with a clean border. It thins gradually, almost reluctantly, as though the galaxy is less an object than a fading zone of influence. This is where the mystery sharpens. The more carefully astronomers look, the less the Milky Way resembles the tidy diagram long presented as settled fact. Space missions begin to deepen the problem. The European Space Agency sends Gaia to map the positions and motions of stars with extraordinary precision. Radio observatories trace hydrogen beyond familiar regions. Infrared observatories look through dust that blocks ordinary starlight. Then James Webb enters the picture, not originally as a machine built to redraw the Milky Way, but as an instrument so sensitive that it starts illuminating parts of the cosmic story that older observatories either blur or miss. Webb sees through dust with unusual power. It resolves faint stars in crowded fields. It reaches into obscured regions where previous surveys lose confidence. Instead of confirming the older shape, the newer data often widen the uncertainty. More stars, more outer structure, more complexity, more reasons to suspect that the Milky Way has been measured by its brightest skeleton, while its fainter body remains largely uncounted. What makes the situation especially strange is that this is not merely a dispute over a margin. It is not a small correction of a few thousand light years. The tension points towards something larger, perhaps twice as large, perhaps even more, depending on how the boundary is defined. That scale of revision is difficult to absorb because it suggests that astronomy may have been speaking with confidence about the size of its own home, while seeing only the most obvious portion of it. A galaxy once taught as a clear spiral disk begins to resemble a layered structure, with no simple perimeter, a bright inner disk, a thicker outer disk, a diffuse stellar halo, streams of stars from consumed dwarf galaxies, vast envelopes of gas, and an enormous dark component that cannot be seen directly at all. If all of this belongs to the Milky Way in some meaningful sense, then the old image is not merely incomplete, it is misleading, and this is where the first deeper unease appears. If the nearest great structure in the universe can be mismeasured by such a wide margin, then the problem is not just local, it hints at something methodological. Humans have been measuring the cosmos outward from a flawed self-portrait. The galaxy serves as a baseline for mass estimates, collision models, satellite dynamics, star counts, and broader comparisons with other spirals. Change the scale of the Milky Way and many other judgments shift with it. The timing of Andromeda's approach changes. The region searched for life expands. The number of stars and planets rises. The amount of missing ordinary matter becomes harder to explain. The role of dark matter grows heavier. A single correction begins to pull on many threads at once. Yet the atmosphere of this discovery remains oddly restrained. There is no clear line where astronomy can say the old Milky Way ends and the new one begins. The evidence accumulates in layers, and every layer produces a new ambiguity. Is the galaxy defined by visible starlight, by gravitational control, by dark matter extent, by bound satellites, by circulating gas, by stellar streams, or by some practical convention chosen for convenience? Each answer gives a different size. The more precisely the question is asked, the less stable the answer becomes. It is this instability that gives the subject its peculiar tension. The Milky Way is not simply growing in the data, it is becoming conceptually harder to pin down. It starts to behave less like a solid cosmic city and more like weather spread across a continent. Webb intensifies that feeling. Its power does not merely reveal new stars. It reveals how much of the previous confidence depends on seeing only the easiest parts. It exposes the hidden cost of drawing clean borders around diffuse structures. It also raises a larger possibility, one that does not fully emerge yet but waits at the edge of the narrative. If the nearest large structure is more extended, more layered, and more elusive than earlier astronomy believed, then perhaps this pattern is not confined to the Milky Way. Perhaps the deeper universe is also full of boundaries drawn too soon. Perhaps astronomers have mistaken the brightest beginnings of structures for their true beginnings, and the brightest endings for their true limits. That thought is still only a suspicion here, but it already changes the mood. The story is no longer just about a galaxy becoming larger. It is about a discipline discovering that its most familiar map may have been built from partial light. And once that possibility takes hold, even the oldest and most sacred measurements of cosmic history begin to feel less settled than they once appeared. The Milky Way is supposed to be the known backdrop, the one thing close enough to anchor the rest of the universe. Instead, it starts to slip. Its edge moves outward, its mass grows, its faint regions brighten into existence. Its hidden structure begins to matter more than its visible form. Home becomes uncertain, and uncertainty at home has a way of spreading outward into every other claim. The first crack in the story is simple enough to state. The galaxy is larger than expected. The harder truth is that astronomers may not yet know what part of the galaxy they have truly been measuring, and if they do not know that with confidence, then the darkness beyond the old map is not empty at all. It is a warning that the universe keeps extending just past the point where certainty ends. The deeper problem is not that the Milky Way is large. The deeper problem is that it is being measured from inside itself. That single circumstance turns an ordinary astronomical task into something closer to reconstruction from fragments. When astronomers study a distant spiral galaxy, they can step back in the only way available to science. They gather its light from afar, they see its outline, its tilt, its bright core, its winding arms, its dark lanes, and its general extent against the black background beyond it. The whole object appears at once, compressed by distance into a shape that can at least be described before it is fully understood. The Milky Way offers no such mercy. It surrounds the observer. Its nearest stars are scattered in every direction. Its dense dust clouds block long stretches of sight. Its bright inner regions glare through layers of gas and crowded stellar populations. Its outer structures lie behind confusion rather than emptiness. Measuring it becomes less like looking at a galaxy and more like trying to infer the shape of a forest while standing deep among its trees at night. The difficulty begins with line of sight. The solar system sits far from the galactic center, in the disk, within a local spur connected to larger spiral structure. That location is not terrible for survival, but it is inconvenient for geometry. Looking inward means staring through dense regions full of dust and overlapping stars. Looking outward means peering through thinner areas where the galaxy seems to fade even when it may simply be growing sparse. In either direction, the view is filtered by location. A clean map is impossible because every observation begins inside the object being mapped. The oldest efforts rely on what can be counted directly. Astronomers chart bright stars. They trace star clusters. They study Cepheid variables, those pulsating stars whose rhythm reveals their distance. They map globular clusters and use their distribution to infer where the center of the galaxy lies. Over time, a picture emerges. It is far better than guesswork, but it is still a picture built from selected lights in a crowded interior. much of the galaxy remains hidden behind dust, especially in visible wavelengths. Some regions look empty because the light never reaches the telescope. Other regions look crowded because many layers of stars overlap in the same field. The illusion of structure and the loss of structure happen at the same time. This is why the Milky Way resists easy boundaries. A distant galaxy can be photographed in full, but the home galaxy has to be assembled from directions, velocities, brightness estimates, chemical clues, infrared penetration, radio emission, and statistical models. It is pieced together the way a buried city is reconstructed from walls, tools, bones, and disturbed earth. No single observation reveals the whole. Everything depends on synthesis. That method works, but it also creates danger. If early assumptions are too simple, later interpretations inherit the error and carry it forward. For decades, the most practical boundary is the visible disk. That is where the star density drops enough for the galaxy to seem finished, but the drop is gradual, not abrupt. Dimmer stars continue beyond the familiar bright zone. Gas extends farther. Halo stars orbit well outside the main disk. Streams of stars from destroyed dwarf galaxies curve through space at astonishing distances. The farther the instruments improve, the more the old edge begins to resemble a convenience rather than a frontier. The change in perspective comes partly from wavelength. Visible light is only one version of the galaxy. Infrared light passes through much of the dust and reveals stars in hidden regions. Radio observations trace cold hydrogen, the raw material from which future stars may form, showing extended structure where visible light finds little. X-ray observations detect hot gas in the surrounding halo. Each wavelength adds another layer, and each layer alters the apparent size of home. A galaxy that looks compact in visible starlight becomes much broader in hydrogen and broader still in its gravitational domain. That difference matters because astronomy has a habit of letting the brightest part of a structure stand in for the whole. James Webb enters this story with unusual force. Its main purpose lies far beyond mapping the Milky Way. It is built to study the early universe, the first galaxies, the atmospheres of distant worlds, the faint infrared glow of structures that Hubble and ground-based telescopes cannot easily resolve. But an instrument this sensitive does not remain politely confined to its original role. Webb sees through dust with a clarity that changes the feeling of the inner galaxy. Regions that once looked like confusion begin to separate into stars, filaments, clusters, and background structure. Fields once treated as heavily obscured become readable. The result is not a clean final map, it is something more disruptive. It reveals how much has been hidden in plain sight by the limitations of older light. Gaia transforms the other half of the problem. It does not merely look, it measures movement, position, distance, and motion across vast star samples begin to converge into a dynamic portrait rather than a static one. A static portrait can mislead because bright regions dominate it. A dynamic portrait forces the galaxy to reveal its mass distribution. Stars orbit at speeds that depend on what is pulling on them. Halo stars and streams preserve the memory of past mergers. Satellite galaxies swing through space as though they are tethered to a much larger invisible structure than the eye suggests. When Gaia data are combined with radio maps, infrared observations, and computer modelling, the Milky Way starts to behave less like a 100,000 light-year spiral and more like a layered system whose true extent depends on what, exactly, is being asked. There is the stellar disk, there is the thick disk, there is the stellar halo, there is the hot gaseous halo, there is the dark matter halo. None of these end in the same place. None offer a universally satisfying boundary. This produces a subtle but serious scientific unease. The word galaxy sounds singular and solid, Yet the real Milky Way is a stack of overlapping components with different scales, different histories, and different degrees of visibility. The disk contains ongoing star formation and familiar spiral structure. The halo contains ancient stars on odd orbits. The gaseous component circulates material outward and back inward over immense timescales. The dark matter component surrounds all of it and shapes the motion of everything, while refusing all direct detection. The farther one moves from the bright centre, the less obvious it becomes which component deserves to define the edge. Astronomers use practical terms to cope with this. One boundary may refer to visible starlight. Another may refer to the radius inside which matter is gravitationally bound in a stable way. Another may refer to the larger dark halo inferred from simulations and observations. Each is defensible. None feel complete. This is why the old confidence now looks fragile. The earlier Milky Way is not exactly false, it is partial. It is the bright Milky Way, the easy Milky Way, the version that older techniques can hold without too much ambiguity. But the hidden Milky Way, the faint and extended one, keeps pressing outward from the data. It reveals that home is not merely a disk of stars but an empire of influence, with a visible centre and an increasingly uncertain edge. The more the measurements improve, the more the galaxy resembles a gradient rather than a shape. That has consequences beyond cartography. If the Milky Way is being reconstructed from the inside with so much difficulty, then every comparison built on that reconstruction inherits some uncertainty. Mass estimates for the local group change. Models of how dwarf galaxies orbit change. The count of stars and planets changes. The timeline for the encounter with Andromeda may change. Even the search for life is quietly altered, because a larger galaxy means a larger inventory of stars, worlds, and chemically varied environments. Yet the most unsettling consequence lies elsewhere. Measuring the Milky Way from within becomes a kind of warning about cosmology itself. The observer is never outside the universe either. The same limitation exists on the larger scale. Human beings do not step beyond the cosmos and inspect it from a distance. They infer its structure from within, through light filtered by time, expansion, dust, selection effects, and the reach of instruments. The Milky Way becomes a local version of that larger predicament. It shows what happens when a system is too large, too layered, and too immersive to be seen all at once. It becomes easy to mistake the visible framework for the full structure. It becomes easy to draw clean borders where none exist. It becomes easy to teach certainty long before the deeper components are understood. So the question in this section is not simply how large the Milky Way is. It is how any civilization inside a galaxy can ever know with confidence where home ends. The answer, at least for now, seems to be that it cannot know cleanly. It can refine, compare, simulate, infer, and revise. It can peel away the dust with infrared light and chart the motions of stars with exquisite precision. It can trace hydrogen far into the outskirts and read the pull of invisible mass through orbit and speed. But even with all of that, the galaxy does not stand still for inspection. It fades outward, component by component, until the concept of an edge becomes a matter of choice. And that choice, once exposed, becomes the first real mystery. It suggests that the Milky Way has not merely been underestimated. It suggests that the very idea of measuring a galaxy from the inside may carry a built-in blindness, a tendency to believe the nearest visible answer before the faintest and most important structures have had time to emerge. The first truly persuasive witnesses do not look important at all. They do not blaze like spiral arms or dominate the sky like a galactic core. They appear as faint, stretched arrangements of stars, so thin and so widely dispersed that earlier generations of astronomers often treat them as background debris, minor irregularities, or statistical clutter. Yet these dim structures, now called stellar streams, become some of the clearest evidence that the Milky Way is larger and more complicated than its old map allows. They are not decorative features, they are the remains of destruction. Each stream begins as a smaller galaxy, or a dense star cluster that wanders too close to the Milky Way and falls under its tidal pull, meaning the difference in gravity from one side of the object to the other becomes strong enough to pull it apart. The process is slow, not explosive. The smaller system stretches, loosens, unravels, and finally spills its stars into long luminous trails. The original body fades, but the orbit remains written across the sky. That orbit is the clue. A stellar stream is not simply a scatter of stars, it is a path shaped by gravity. The stars within it are moving through the Milky Way's gravitational field, and their motion records the mass distribution that guides them. This is why streams become so powerful. A bright disk can mislead. Dust can hide stars. Visible boundaries can look sharper than they are. But a stream follows the pull of the galaxy, whether that pull comes from luminous stars, cold gas, or invisible dark matter. It is a kind of honest testimony. It cannot be explained away by surface brightness alone, because its very existence depends on the full depth of the gravitational landscape. Once astronomers begin to take these streams seriously, the older picture of the Milky Way starts to weaken more rapidly. The Sagittarius stream becomes the most famous example. It originates from the Sagittarius dwarf spheroidal galaxy, a small companion that is still in the process of being destroyed by the Milky Way. Its stars do not remain near the dwarf. They wrap around the galaxy in immense loops, like threads thrown around a spinning wheel. This is already strange enough. A galaxy is eating another galaxy in the present age of the universe, and the meal is leaving a ring of evidence around the entire host. But the deeper surprise lies in the scale. The stream reaches distances that sit well beyond the traditional bright edge of the Milky Way. If those stars are still tracing orbits controlled by the Milky Way, then the galaxy's gravitational domain must extend far beyond the familiar disk. This is not a matter of taste, it is a matter of dynamics. The stars are there. Their motions are measurable. The force required to hold them in such paths cannot come from a small galaxy pretending to be large. Other streams add to the tension. The stream called GD1 appears as a thin stellar ribbon in the halo, remarkably narrow and orderly, as though the remains of some older system have been drawn through a giant invisible comb. The orphan stream is even more haunting, a name born from uncertainty because astronomers are not initially sure what parent object created it. It drifts through such distant and unusual regions that for a time it seems barely connected to the Milky Way at all. Yet its motion, when examined carefully, suggests that it too belongs to the galaxy's broader gravitational structure. That is the unsettling pattern. One by one, streams appear in places that feel too remote, too sparse, too close to intergalactic emptiness. Yet the mathematics keeps pulling them back into the Milky Way story. The galaxy does not stop where the bright spiral disk fades. It keeps exerting order far beyond that border, and the streams expose this quiet reach. What makes these structures scientifically valuable is their sensitivity. A stream does not merely say that gravity exists, it reflects the shape of the gravitational field. If the field is smooth, the stream follows one sort of path. If the field is lumpy, stretched, asymmetric, or disturbed by passing masses, the stream bends, thickens, breaks, or wrinkles. In recent years, astronomers have used Gaia data, deep sky surveys, and careful modelling to read streams almost like seismographs of the galactic halo. Small disturbances in a stream may hint at concentrations of dark matter. Missing segments or strange gaps may point to past encounters. Unexpected curves may imply that the Milky Way's mass is distributed differently than earlier models assumed. Every stream is both a ruin and a measuring device. This is where the mystery changes character. At first, the Milky Way merely seems bigger than expected. With stellar streams, it begins to seem less settled than expected. The halo is not empty. It is full of motion, debris, memory, and structure. The galaxy is not a calm spiral floating in space. It is the product of repeated collisions and absorptions, a system still digesting its past. Streams reveal that history with unusual honesty because they are not theoretical constructions. They are torn remnants of real objects whose stars continue to orbit long after the parent body is undone. In that sense, the outer galaxy is not a clean edge at all. It is a graveyard of mergers, a region where former galaxies continue to circle as elongated scars. The more such scars are found, the harder it becomes to treat the Milky Way as a single smooth disk with a neat diameter. It starts to resemble a layered archaeological field where every faint arc marks a previous conquest. That has consequences for size. If a stream circles at a distance of well over 100,000 light-years and still behaves as a bound feature of the Milky Way, then the galaxy's effective extent must include the region guiding that motion. Some astronomers prefer to distinguish between the visible stellar disk and the wider halo. That is reasonable, but it does not remove the main implication. The old textbook number begins to look like the size of only one layer, not the whole system. The streams make that difficult to ignore because they turn empty-looking space into evidence of control. The galaxy is claiming regions it does not brightly illuminate. It is present where it does not obviously shine. That is precisely the kind of detail earlier astronomy is most likely to miss. James Webb intensifies the general shift, though not always by finding streams directly in a single dramatic gesture. Its greater role is to make faint structure across dusty or crowded regions more legible, and to improve the broader understanding of stellar populations and hidden complexity. Gaia does the same from another angle, by measuring motions with extraordinary accuracy. Together with ground-based surveys, these tools transform stellar streams from faint curiosities into one of the best traces of the Milky Way's outer architecture. Older sky maps often glimpse such features only partially. Newer data begin to reveal their continuity. What once looks like isolated patches becomes a coherent loop. What once looks like a local anomaly becomes the edge of a much larger stream. And once the full path is reconstructed, the required scale of the galaxy expands again. There is also a more speculative unease attached to streams. Because they are sensitive to the invisible mass around them, they raise the possibility that the halo is not smooth at all. Standard dark matter models often predict smaller clumps of invisible matter orbiting within larger halos, a kind of substructure that should perturb streams as it passes. In some stream data, astronomers do find gaps and irregularities that may be consistent with such dark clumps. The evidence is not final, and other explanations remain possible, but the idea is difficult to dismiss. If true, the outer Milky Way is not merely larger than expected. It is populated by hidden concentrations of mass, structures with no light of their own, moving through the halo and leaving only disturbances in the paths of already dead galaxies. That possibility pushes the mood from correction into something stranger. The galaxy becomes a place where the invisible shapes the visible from behind the scenes. A stream can then be read almost like a piece of torn fabric drifting through a dark machine. The folds and missing pieces reveal the machine's hidden gears. Another unsettling feature of stellar streams is their timescale. These are not short-lived accidents. A stream can persist for billions of years, preserving the echo of an encounter from a very different era of the galaxy's history. Some of the stars now arcing through the Milky Way halo may once belong to dwarf galaxies that no longer exist as separate systems. Their home is gone, but their orbital memory remains. In a deeper sense, the outer Milky Way is filled with displaced populations, captured stars still moving according to histories that begin elsewhere. The galaxy's size is therefore tied to violence. It grows not only by quiet star formation, but by expansion through accretion, by taking other systems apart and keeping their stars, clusters, and dark matter. Streams are the visible proof of that process. They do not merely indicate where the galaxy is, they indicate how it became what it is. That history matters because it suggests the Milky Way is not static. A size estimate is not measuring a finished object. It is measuring a structure still forming through mergers, still reshaping itself through orbital mixing, still extending its influence through gravity. The boundary may therefore be fuzzy not simply because observations are hard, but because the galaxy itself is intrinsically diffuse and historically layered. There may never be a single clean answer because the Milky Way is not built like a solid body. It is built like accumulated weather, long after the storms that made it have passed. By the time this becomes clear, the streams have already done their work. They have turned the outer darkness from absence into evidence. They have shown that the faintest features may carry the strongest testimony. They have also introduced a new pattern that will keep deepening in the sections ahead. The universe often hides its most important truths in what first appears to be debris. Ruins become rulers, fragments become maps. Destroyed galaxies become the instruments by which the living galaxy is measured, and the answer they keep pointing toward is uncomfortable in its simplicity. Home is larger than expected because its gravity keeps reaching into places where the old diagrams say nothing should still belong to it. The Milky Way is not ending where it was supposed to end. It is still holding on far out in the dark, and the dead stars circling there are the ones that reveal it. The moment dark matter enters the story, the Milky Way stops behaving like an object that can be judged by sight alone. Its spiral arms, bright star clouds, glowing nebulae, and crowded central bulge remain real enough, but they begin to look like the visible surface of something much larger, heavier, and less direct. For decades, the basic clue has been simple. Stars in the outer parts of galaxies move too fast. If only the visible mass existed, many of those stars should drift outward or escape entirely. Instead, they remain in orbit, as though an unseen hand keeps closing around them. This pattern is not unique to the Milky Way. It appears across spiral galaxies in general and becomes one of the main reasons astronomers infer dark matter in the first place. Yet in the case of the Milky Way, the inference becomes especially intimate. The invisible structure is not merely out there in some distant galaxy. It is here, surrounding the solar system, passing through the disk, shaping the orbit of the Sun, holding faint halo stars in place and extending far beyond the old bright boundary. The visible galaxy now begins to look like the inner lantern of a much larger dark body. The older picture is easy to understand. There is a disk of stars, gas, and dust roughly 100,000 light-years across. Perhaps a little more depending on the wavelength and the exact edge chosen. Surrounding it is a less luminous halo of ancient stars and globular clusters. Beyond that lies intergalactic space. It is a neat sequence. Dark matter ruins that neatness. Once astronomers begin mapping rotation speeds and orbital motions more carefully, the visible mass is no longer enough to explain what the galaxy is doing. The simplest explanation is that the Milky Way sits inside an extended halo of matter that neither emits nor absorbs light in the ordinary way. This material interacts primarily through gravity. It does not announce itself through glow or heat. It announces itself through influence. The influence is immense. Most estimates suggest that the Milky Way contains far more dark matter than ordinary visible matter. The exact ratio depends on the model, the radius considered, and the method used. But the broad conclusion is stable. Most of the galaxy's mass is invisible. That means the part humans actually see. The part turned into textbook illustrations and planetarium panoramas is only a thin inner concentration inside a much larger gravitational structure. The old map suddenly becomes misleading in a very specific way. It is not that the Milky Way is falsely drawn as a spiral. It is that the spiral is treated as the whole when it may be only the bright centre of the whole. Once this is understood, the question of size changes entirely. A galaxy can no longer be measured only by where starlight fades. It has to be measured by what remains bound to its gravity. That is where terms like virial radius begin to matter. The phrase sounds technical, but the underlying idea is plain. It refers to the broader region inside which matter behaves as part of the galaxy's gravitational system, rather than drifting independently through the wider universe. That region is usually much larger than the bright disk. In many models for the Milky Way, it extends on the order of a few 100,000 light-years, not 100,000. Some calculations push the effective dark matter halo farther still, depending on where one chooses to stop counting an ever-thinning density profile. That is the first unsettling consequence. The galaxy may already have been far larger than the old number even before newer stellar evidence and more refined measurements began pushing the visible and semi-visible components outward. The second consequence is stranger. Dark matter halos do not have crisp edges. Their density decreases gradually. The farther outward one goes, the more arbitrary the boundary becomes. If a visible disk can mislead because it ends gradually, a dark halo misleads even more because it may not truly end in any clean observational sense at all. It just becomes weaker, thinner, harder to distinguish from the background structure of the universe. This makes the Milky Way feel less like a single object and more like a fading territory. It has a crowded centre, a structured middle, a sparse halo, a larger invisible envelope, and then a transition into broader cosmic matter distribution. The old need for a definite diameter begins to look like a human preference imposed on a system that does not honour hard borders. Yet astronomers still need working definitions, and every working definition carries consequences. If the Milky Way's gravitational domain reaches out to roughly 200,000 light-years or more, then satellite galaxies once thought to be distant neighbours may actually be deep inside its sphere of control. Stellar streams that look isolated may turn out to be native features of its halo. Gas far from the bright disk may still be part of its recycling system. Even the timing of Andromeda's future interaction with the Milky Way becomes less straightforward, because the first contact between galaxies may happen when their dark halos begin to overlap, long before their visible disks approach each other. In that sense, dark matter changes not only size but chronology. It moves events earlier than the eye would suggest. The hidden galaxy begins acting before the visible galaxy arrives. James Webb's role in this broader shift is subtle but important. Webb does not detect dark matter directly. No telescope does. But by revealing faint stellar populations, resolving obscured structure, refining views of dust-filled environments, and expanding the known complexity of galactic outskirts, it strengthens the case that the visible Milky Way is incomplete in ways older data underestimate. At the same time, Gaia and other surveys track stellar motions with such detail that the invisible gravitational framework becomes harder to ignore. The visible stars behave as though embedded in something larger. It is the combination that matters. One instrument sees deeper into the faint or hidden luminous parts, another measures motion with extraordinary precision. Together they make the dark halo feel less like an abstract theoretical patch and more like the missing body around the galaxy's visible skeleton. This has an emotional effect on the story as well. The Milky Way becomes stranger not because it contains something exotic at its edge, but because it may be made mostly of something that cannot be seen anywhere. Human beings find themselves living inside a galaxy whose dominant substance is inferred rather than observed. The sun, the planets, the glowing dust clouds, the billion points of starlight in the night sky. All of it may amount to a minority component. The true architecture is dark. The familiar universe is suddenly demoted to ornament. That inversion is difficult to absorb because it runs against the deepest habit of vision. It suggests that what looks substantial is secondary, and what cannot be seen is primary. There is also a more delicate mystery lurking inside the halo itself. Dark matter is often treated as smoothly distributed in large-scale models, but observations and simulations alike leave room for clumps, asymmetries, and substructure. The Milky Way has grown by mergers. It continues to absorb smaller systems. Its halo may therefore be filled with remnants, denser regions, tidal distortions, and invisible concentrations moving through it like submerged weather fronts. If that is true, then the outer galaxy is not just a quiet spherical cocoon. It is a dynamic region full of past collisions and hidden architecture. Some stellar streams may already be hinting at this through their unexplained gaps and bends. Some satellite motions may point to a gravitational field that is not perfectly smooth. None of this is settled in a final way, but the possibility changes the tone. The halo becomes a place of quiet complexity, perhaps even of invisible terrain. The idea that the Milky Way might be twice as large as once believed now starts to feel almost too simple. The deeper change is conceptual. The galaxy is no longer a brightly bounded spiral with a little extra mass around it. It is a vast invisible halo within which a spiral happens to shine. That shift reverses the order of importance. The visible disk becomes the local concentration, the inner event, the region where ordinary matter cooled enough to make stars and planets. The larger structure, the one doing most of the holding, remains dark. In practical astronomy, this affects nearly everything. A larger and more massive halo can bind more satellites, influence more streams, contain more hot gas, and shape a broader neighborhood. It changes estimates of how the Milky Way interacts with the local group. It affects simulations of galaxy growth. It alters ideas about how much ordinary matter should be present and where it might be hiding. It even reshapes the imagined geography of the night sky, because the visible river of stars seen from Earth is now recognized as only the inner glow of something extending vastly farther into invisibility. This is also where the sense of mystery begins to widen beyond the Milky Way. If the home galaxy has been represented for generations mainly by its luminous center, while its actual gravitational body lies much farther out, then the same may be true of galaxies throughout the universe. Astronomers may have been cataloguing the bright cores of systems while underestimating the full reach of their halos. The correction that begins at home may not stay at home. It may spread outward into the cosmic census itself. But even before that larger implication takes hold, the Milky Way alone is enough to alter the mood. The galaxy is no longer simply big. It is layered, dominant, and partially hidden by its own nature. It does not stop where the stars stop. It does not reduce to the graceful spiral presented in a diagram. It surrounds that spiral with a region of invisible control that reaches out into darkness, holding ancient streams, dwarf companions, fast-moving halo stars, and perhaps vast stores of missing matter. The visible Milky Way turns out to be the bright confession of a darker whole, and that whole keeps expanding every time astronomy learns to trust gravity over appearance. The next correction does not come from the main body of the galaxy at all. It comes from the things circling it. The Milky Way is not alone in space, not even locally. Around it move smaller systems, some bright enough to be known for centuries, others so faint that they emerge only through careful modern surveys. These are the satellite galaxies, and for a long time they seem like companions, ornaments, lesser neighbours moving around a larger centre. But as their motions become clearer, they begin to reveal something far more consequential. They do not simply decorate the Milky Way, they measure it. Every orbit carries information about the gravitational field that holds it. Every speed, every distance, every elongated path through the halo becomes a clue about the true size and mass of the host galaxy. In this way, the Milky Way's outer empire begins to declare itself not through its own light, but through the obedience of other galaxies. The most familiar satellites are the Large Magellanic Cloud and the Small Magellanic Cloud, visible from the southern hemisphere as detached patches of misty light. To the eye they seem modest, almost harmless, smaller galaxies drifting nearby. In reality they are substantial systems with their own stars, gas, history, and internal structure. They are not insignificant bodies, they are galaxies in their own right, caught in the neighbourhood of a larger power. For a long time their future remains uncertain in older models. Are they only passing through? Are they bound to the Milky Way permanently? Or are they brief visitors on a wider cosmic track? The answer matters because a bound satellite implies a deep gravitational well. To hold such objects at their distances, the Milky Way must be more massive than its visible stars suggest. A lighter galaxy would not keep them so effectively. A heavier one could. As better measurements of their motion arrive, the argument tilts toward a more massive and more extended Milky Way. The clouds are not merely nearby, they are caught. Other satellite galaxies deepen the pattern. The Sagittarius dwarf, already being torn apart into a great stream of stars, is the most dramatic example because it turns orbital captivity into active destruction. But beyond Sagittarius lie many smaller companions, systems like Draco, Ursa Minor, Sculptor, Carina, Fornax, and a growing list of ultra-faint dwarfs found in modern sky surveys. These dim objects are easy to miss because they contain relatively few stars and spread them thinly across the sky. In older observations, many of them blur into insignificance, almost into invisibility. Yet their importance grows with every improvement in data. Each dwarf galaxy has a location, each has a velocity, each moves as though it belongs to a much larger gravitational environment than the bright Milky Way alone could provide. Some sit at distances that once feel almost too far to count as true satellites. Yet if they are bound, then the Milky Way's reach must already extend into regions once imagined as the beginning of open intergalactic space. This is how space itself begins to shrink conceptually. The visible gap between galaxies is no longer empty in the old sense. It becomes contested territory, a region filled with extended halos, tenuous gas, disrupted streams, and the orbits of small captive systems. The Milky Way's neighbourhood grows crowded not because new galaxies are physically added, but because the existing ones turn out to inhabit a larger sphere of influence than earlier maps allow. A satellite galaxy is not just an object nearby. It is evidence that the host galaxy's gravity keeps working far beyond the bright disk. The farther out the satellite, and the faster it moves while still remaining bound, the stronger that evidence becomes. This is why the dwarfs matter so much. They are test masses at immense distances. They act out the strength of the Milky Way's pull in regions where direct light from the main galaxy fades almost to nothing. The pattern is difficult to dismiss because it appears again and again. Old estimates of the Milky Way often make the galaxy seem moderate, perhaps even less dominant than Andromeda. Newer orbital reconstructions complicate that picture. A more massive halo can explain why more satellites stay in orbit, It can also explain why some satellite paths are more tightly curved or more deeply trapped than earlier models predict. The Milky Way begins to look less like a modest spiral with a few neighbours and more like a central power maintaining a broad retinue. Yet this word retinue is still too polite. The relation is often violent. The satellites are not merely circling. Many are being stripped, heated, deformed, or dismantled. Gas is drawn away. Stars are pulled into streams. Orbits decay over time. The satellite population then becomes a living record of cannibalism in progress. The Milky Way does not just host smaller galaxies, it consumes them. That matters for measurement because every act of stripping spreads stars and gas farther into the halo, enlarging the region that must still be considered part of the galaxy's broader structure. The Magellanic Stream becomes one of the strangest examples. It is a vast ribbon of gas associated with the Magellanic Clouds, stretching across a huge swathe of sky. This gas is not comfortably contained within the clouds any longer, but neither is it simply detached from the Milky Way story. It exists in between, a transitional feature linking satellite galaxies to the circumgalactic environment of the host. Here the difficulty of defining edges returns in a new form. Does this gas belong to the clouds, to the Milky Way, or to the wider medium between galaxies? It is influenced by all three contexts. It is shaped by motion, pressure, gravity, and past interaction. It refuses a clean category. And once again the outer galaxy begins to feel less like a border and more like a zone of ongoing negotiation. James Webb adds indirect force to this picture by improving knowledge of distant and faint stellar populations, of dust-hidden regions, and of the environments where ordinary starlight once fails. Gaia adds the dynamical precision needed to follow motions more exactly. Together with ground-based instruments and longer-running sky surveys, they allow astronomers to discover more ultra-faint dwarfs and to refine the motion of known ones. That in turn sharpens the map of the Milky Way's gravitational reach. Yet each improvement brings a strange side effect. Instead of stabilizing the edge, it often pushes the edge outward again. New dwarf candidates appear in the data. Some turn out to be genuine galaxies. Others turn out to be disrupted remnants. Either way, the outskirts of the Milky Way become more populated and more active than expected. The outer halo is no longer treated as a mostly empty shell, with a few ancient stars drifting through it. It becomes a dynamic region full of satellites, debris, gas, and invisible mass. This changes the local group as well. The Milky Way and Andromeda are usually imagined as separate giant spirals facing one another across a wide gulf of space. But if both have extended halos and broad satellite systems, the gulf narrows. Dwarf galaxies between them may not belong cleanly to one host or the other. Some may move in a combined gravitational field. Some may shift allegiance over cosmic time. Some may be caught in the early stages of the future encounter between the two giants long before their disks meet. In that sense, the satellites are not just measuring current size. They are tracing future history. Their orbits reveal where the influence of one galaxy begins to overlap the influence of another. They may even hint that what appears as separation in visible light is already less separate in gravitational reality. There is another tension inside this story. Simulations of cosmic structure often predict more small satellite galaxies than astronomers actually observe. This is sometimes called the missing satellites problem. A larger, more massive Milky Way could intensify that puzzle by implying that more dwarfs should exist in its outskirts than have so far been detected. But it also offers a partial resolution. Perhaps many satellites are simply too faint, too diffuse, or too distant to have been found yet. If the Milky Way's domain extends farther than the old bright map suggests, then the search area grows as well. Ultra-faint dwarfs may be hiding in the margins of surveys. Their stars spread so thinly that they almost disappear into background noise. Every time a new one is found, it slightly redraws the outer geography. Every discovery asks the same quiet question. How many others are still there, too dim to notice, circling through darkness at the edge of what is called home? This is where the story acquires a subtle claustrophobia. At first, a larger Milky Way sounds like expansion, like more room, more stars, more worlds, a grander stage. But as the satellites accumulate, the feeling changes. The space around the galaxy does not become empty and generous, it becomes governed. The Milky Way's influence reaches farther than expected, binding companions, stripping them, stirring gas, curving streams, and claiming territory that old maps leave blank. The galaxy starts to feel less like an island and more like a basin, in which smaller systems slowly lose their independence. Its outskirts are not calm, they are full of captured motion, and each orbit, carefully measured, keeps telling the same story. The Milky Way is larger because other galaxies cannot quite get away from it. Their paths bend inward, their gas trails behind them, their stars peel off into the halo. Their existence becomes proof that the galaxy's real boundary is not where its light fades, but where its pull still decides what happens next. The story grows stranger when the larger Milky Way is placed beside Andromeda. For a long time, the future collision between the two galaxies is treated as a remote certainty, a dramatic event far beyond any human timescale, safely confined to the distant future. The usual image is simple enough. Two great spiral galaxies drift toward each other across millions of light-years of apparent emptiness. One day, billions of years from now, their disks distort, their stars reshuffle, their gas clouds collapse into bursts of new star formation, and the local group is remade. In that older version of the story, the collision begins when visible structure approaches visible structure. The eye is given authority. The first contact is imagined as a meeting of starry forms. But once the Milky Way grows in the data, and once its dark matter halo is taken seriously as the dominant component, that familiar timeline begins to slip. The collision no longer starts with light, it starts in darkness. And that possibility changes the emotional weight of the event entirely, because something once described as future tense begins to look as though its earliest phase may already be underway. Andromeda, also known as Messier 31, lies roughly 2.5 million light-years away. In the night sky it looks serene, a faint elongated glow, almost fragile to the naked eye. Yet it is a giant spiral galaxy, comparable to, or perhaps somewhat larger than the Milky Way depending on the model and on which parts are counted. Its visible disk is broad, its own system of satellites is extensive, its dark halo, like that of the Milky Way, likely reaches far beyond what ordinary photographs reveal. Once both galaxies are imagined with these enlarged gravitational bodies, the space between them begins to contract in conceptual terms. The visible disks still remain far apart, but the invisible structures around them may already extend into the same territory. The old empty gulf becomes less empty with every revision. If the Milky Way's effective gravitational domain reaches a few 100,000 light-years, and if Andromeda's does the same, then the truly neutral space between them is not what it appears from starlight alone. The first collision may be happening when nothing obvious shines. This matters because dark matter halos do not behave like solid shells. They are not walls that clang together. They are diffuse, interpenetrating structures whose particles pass through one another almost without ordinary collision, while their combined gravity reshapes the orbits of everything around them. That means the opening stage of a galaxy collision is subtle. It is not fire. It is a change in the gravitational environment. Outer halo stars begin to feel a slightly altered pull. Satellite galaxies drift in fields that are no longer purely local. Gas clouds are nudged. Long-term orbital patterns shift. The disks remain outwardly separate, but the hidden architecture begins adjusting in advance. This is the idea that makes the future merger feel less remote. It suggests that the Milky Way and Andromeda do not wait until their visible stars overlap before interacting. They begin through their halos, quietly and far ahead of the spectacle that textbooks usually emphasize. The evidence for Andromeda's approach is firm. Measurements of its radial motion show that it is moving toward the Milky Way. That part is not speculative. Over cosmic time, the two galaxies will come together. But the exact timetable depends on details that remain uncertain, especially the total masses of the galaxies, the shape and extent of their halos, and the sideways component of Andromeda's motion. Older estimates tend to place the major merger several billion years in the future, with first close passage after about 4 billion years and the final coalescence later still. Newer revisions to the size and mass of the Milky Way do not cancel that broad picture, but they do complicate it. A more massive galaxy exerts a stronger pull over greater distances. A more extended halo means earlier influence. Even if the visible collision remains far ahead, the hidden encounter may begin sooner than once assumed. This is where the sense of anomaly grows stronger. Two galaxies can be colliding before they look as though they are colliding. The eye sees separation. Gravity sees overlap. That distinction has consequences not just for when the event begins, but for what counts as a galaxy in the first place. If a galaxy's identity includes its dark matter halo, its satellite system, its stellar streams, and its circumgalactic gas, then the boundaries between large galaxies may start dissolving long before any bright spiral arm is disturbed. The future merger becomes less an event with a clear starting moment and more a gradual deepening of mutual influence. The local group then stops resembling a set of separate islands and begins to look like a basin in which the largest masses are already shaping one another across distances that human intuition finds absurd. The satellite galaxies between the Milky Way and Andromeda sharpen this point. Some dwarf systems occupy regions that may eventually become contested gravitational territory. Their orbits are not static decorations around one host. Over billions of years they may shift under the combined pull of both giants, be stripped apart, or be flung into new paths as the two main halos continue their approach. In that sense, the smaller galaxies are the first casualties and the first indicators. They inhabit the transitional zone where the notion of separate galactic empires becomes harder to maintain. Triangulum, the third large spiral in the local group, adds another layer of tension. It lies closer to Andromeda than to the Milky Way, and may itself be bound into Andromeda's broader gravitational future. If so, then the coming transformation of the local group is not a simple duel between two equal spirals. It is a more crowded and entangled rearrangement involving halos, satellites, streams, and shared outskirts long before any final merged galaxy appears. When the physics of galaxy collisions is described carefully, it becomes almost more mysterious than dramatic. Stars rarely strike one another directly because the distances between them are enormous. The great violence happens through gravity, orbital distortion, and gas compression. Dark matter halos slide through one another, invisible yet decisive. Gas clouds are compressed, then collapse into new stars. Spiral structure is stretched into tidal tails. Ancient orbits are scrambled. The central black holes eventually approach and merge far later in the process. Nothing about this resembles the ordinary human image of impact. It is more like two weather systems entering the same atmosphere, except the atmosphere spans millions of light years and the consequences take billions of years to unfold. Yet scale does not make the process less real. It only makes it harder to feel. The correction to the Milky Way's size changes that feeling, because it brings the opening phase closer, at least conceptually. The galaxies stop waiting at a polite distance and begin influencing one another through their unseen mass. There is also a more speculative edge to this story, and it arises from the fact that astronomers are still refining halo shapes and total masses. If the Milky Way is larger and more massive than once believed, what if Andromeda is too? The same biases that keep the home galaxy's edge too small may also affect the neighbour. Andromeda is easier to observe as a whole because it is external, but that does not mean every faint outer structure is already fully measured, or that its dark halo is perfectly constrained. If both galaxies have been somewhat underestimated, then the zone of overlap between their broader gravitational domains may be larger than older models suggest. The future collision would not necessarily become immediate in any ordinary sense, but its prehistory would deepen. The idea that the halos may already be touching becomes harder to dismiss as mere metaphor. This does not mean astronomy has caught the Milky Way and Andromeda in a visible embrace. It means the definition of contact may need revision. Contact might begin where stars do not announce it. Contact might mean the first measurable alteration of outer motions, the first large-scale sharing of gravitational territory, the first quiet distortion in halo structure. And if that is accepted, then the collision is no longer a clean future event. It becomes a process with a hidden beginning, already extending into the present age of the universe. That thought widens the mystery in a subtle way. It suggests that human beings may already live inside the earlier stage of one of the largest future transformations their galaxy will undergo, yet perceive none of it directly because the decisive structures are dark and diffuse. This quiet beginning also changes the meaning of home. The Milky Way is not only larger than expected, it may already be in conversation with Andromeda through forces that ordinary starlight does not reveal. The night sky remains calm. The visible river of stars above Earth gives no warning. Andromeda still appears as a faint oval in autumn skies. Nothing in everyday human perception suggests that the great neighbour is already participating in the Milky Way's deeper gravitational future. Yet on the scale of halos and billions of years, the first stage may already have begun. The galaxies are not yet colliding in the way popular imagination expects, but they may already be leaning into one another in the dark, and the larger the Milky Way becomes, the less that possibility feels like speculation, and the more it feels like the hidden truth beneath an apparently quiet sky. Once the Milky Way expands in size, another problem rises behind it almost immediately. A larger galaxy is not only wider, it is heavier. More distant streams, faster halo stars, farther satellites, and a broader dark halo all point toward a deeper gravitational well. That means the old mass estimates begin to look incomplete in the same way the old diameter does. The galaxy does not merely gain more territory in the maps, it gains weight in the equations, and that added weight creates a peculiar chain reaction. Every increase in total mass improves one set of mysteries while worsening another. The outer motions make more sense, but the inventory of matter becomes harder to balance. The star count rises, but the missing ordinary matter becomes more conspicuous. The galaxy looks more complete in one direction, and less complete in another. This is the part of the story where correction turns into multiplication of uncertainty. For many years, the Milky Way is described as containing on the order of a few 100 billion stars and a total mass dominated by dark matter. Perhaps around 1 trillion solar masses or somewhat more, depending on the method. Those numbers are never perfectly fixed, but they live within a familiar range. Then better modelling of stellar streams, dwarf galaxy orbits, escape velocities, halo structure, and gas distribution begins to nudge the total upward. Some studies remain conservative, others argue for a much heavier galaxy. The exact value remains debated, but the direction of change is clear enough to unsettle old confidence. If the Milky Way is larger, more extended, and more successful at holding distant objects than older models allow, then it is probably more massive as well. That mass does not appear evenly in visible form. Most of it still belongs to dark matter. But even a shift in the total has consequences for ordinary matter, because cosmology predicts roughly how much normal material should accompany a galaxy of a given scale. When the galaxy gets heavier, the expected inventory of ordinary matter rises too, and that is where the next puzzle opens. Ordinary matter is the familiar kind, the material that makes stars, planets, gas clouds, dust grains, living cells, and telescopes. In the Milky Way, it should not be especially mysterious. It shines, absorbs, cools, heats, forms structure, and leaves chemical fingerprints. Yet when astronomers count the visible stars, the cold gas, the warm gas, and the dust, they keep coming up short. A substantial fraction of the expected ordinary matter is hard to find. This is not the famous dark matter problem. Dark matter is invisible by definition and is inferred through gravity. The missing ordinary matter problem is stranger in a quieter way because the missing material is supposed to be the normal kind, the very kind from which observers themselves are made. The larger the Milky Way becomes, the more of that ordinary matter should exist somewhere in or around it, and the more uncomfortable its absence becomes. Some of it is almost certainly not absent at all, only difficult to detect. Hot gas in the circumgalactic medium, the vast region surrounding the visible galaxy, is one likely hiding place. This gas can be so thin and so energetic that it evades easy measurement. It does not shine in the same convenient way as stars. It can be detected indirectly through X-rays, through absorption signatures in the light of distant quasars, and through other subtle methods. But not with the comforting clarity of a star field. Observations over the past decades have indeed revealed that galaxies are surrounded by significant envelopes of hot, diffuse gas. The Milky Way is no exception. Yet even with that reservoir included, the accounting remains uneasy. A larger galaxy should host more ordinary matter than older measurements can comfortably trace. The inventory improves, but the books still do not close. At the same time, the number of stars may itself be rising. This is not because new stars suddenly appear, but because more of the outer galaxy turns out to contain real stellar populations that old surveys either miss or underestimate. The traditional figure of roughly 200 billion stars begins to look less secure. A broader galaxy with an extended disk, a richer halo, absorbed dwarf remnants, and wider regions of faint red dwarfs could contain many more, perhaps several 100 billion in total. The exact number remains uncertain because counting stars in a dusty layered galaxy is an exercise in extrapolation. Astronomers sample regions, estimate densities, classify populations, and then scale those measurements across volumes that grow less familiar the farther out they go. But this much is clear. When the galaxy doubles in effective diameter, even if the outermost regions are much sparser than the inner disk, the available volume grows tremendously. Thinly scattered stars still add up. Faint populations still count. The outskirts begin to matter statistically in a way older textbook diagrams barely suggest. This is where the story acquires a new emotional texture. A larger galaxy means more stars, more planets, more possible histories, more buried remnants of devoured systems. It sounds expansive, almost generous. Yet the same increase sharpens the sense that astronomy is working with incomplete ledgers. More stars imply more ordinary matter locked into long-lived red dwarfs, stellar remnants, rogue planets, dust, and gas. More mass implies more dark scaffolding. More halo implies more places for hot material to hide. The Milky Way begins to resemble an estate whose visible buildings occupy only a fraction of the land, while the records of ownership, population, and buried resources remain scattered and contradictory. One clue comes from the fastest stars. Halo stars moving near escape velocity are especially useful because their speed constrains how much mass lies inside their orbit. If these stars remain bound to the galaxy, then the galaxy must be heavy enough to keep them. Gaia has transformed this part of the field by giving astronomers a far better census of stellar motions, especially in the solar neighbourhood and beyond. Some stars appear to be racing so close to the edge of escape that a small revision in their measured speed or in the galaxy's mass changes their fate entirely. Bound or gone, resident or exile. These stars become test particles for the galaxy's gravitational depth, and repeatedly they suggest a Milky Way that is not light, not modest, not easily defined by the visible disk. The galaxy is deeper than it looks, yet even here uncertainty multiplies. A faster star may point to a heavier halo, but a heavier halo means more expected ordinary matter. A broader halo means more room for hot gas reservoirs, undetected dwarfs, dim stars, and ancient debris. The moment one puzzle relaxes, another tightens. There is also the question of how much of the outer stellar halo comes from the Milky Way's own early star formation, and how much comes from consumed galaxies. The answer is probably both. The halo is not a pure native population. It is a mixture, a record of mergers layered over the original galaxy. Some of the stars now counted as part of the Milky Way did not form in it. They belong to smaller galaxies that were later absorbed. That means the star count is not only a matter of current structure, it is also a matter of history. The Milky Way has grown by acquisition. Every stellar stream, every disrupted dwarf, every chemically distinct halo population is a reminder that the galaxy builds itself by taking matter from elsewhere and redistributing it into a wider whole. A larger Milky Way is then not merely a bigger version of the old one. It is the cumulative product of repeated addition, stripping, heating, and rearrangement. In a sense, its uncertain mass and star count reflect not just imperfect measurement, but an unsettled biography. James Webb contributes to this atmosphere by seeing faint structures and obscured populations that sharpen the feeling that the visible inventory is incomplete. It does not solve the missing ordinary matter problem by itself, nor does it deliver a final star count, but it intensifies the general pattern. The more sensitive the instrument, the more complex the galaxy becomes. Dusty regions reveal hidden clusters and protostars. Faint outskirts reveal stars where emptiness was expected. Distant galaxies elsewhere in the universe reveal that diffuse structure is easy to underestimate. The lesson keeps repeating at multiple scales. The brightest material is the easiest to count, and the easiest to count is rarely the whole story. This is also where the search for life quietly changes. More stars mean more planetary systems. Even conservative exoplanet statistics imply that planets are common, and that many stars host multiple worlds. A larger Milky Way therefore carries a larger inventory of possible habitable environments. But here too, abundance increases tension rather than resolving it. If the galaxy contains more stars and more planets than earlier estimates suggest, then the silence around intelligent life becomes more striking, not less. The Fermi paradox. The unease produced by a seemingly empty sky in a galaxy that ought to host many opportunities for life does not disappear, it sharpens. The bigger the census becomes, the more unusual the quiet feels. Yet that question remains suspended in the background for now, because another silence feels even closer. Half of the ordinary matter is still difficult to account for. The galaxy becomes an enormous structure made mostly of invisible dark matter, filled with hundreds of billions of stars, wrapped in diffuse hot gas, and still somehow missing a substantial share of the ordinary material that should belong to it. The scale keeps growing, but the accounting never settles. Every revision toward a larger Milky Way therefore carries a double message. The galaxy is richer than expected, and the galaxy is less understood than expected. It is heavier, but not fully inventoried. It is more populous, but not fully counted. It offers more places for worlds and more evidence of ancient mergers. Yet it also conceals ordinary matter so effectively that astronomers must hunt for it at the limits of detection. In the end, the mass of the Milky Way becomes more than a number. It becomes a measure of how much of home remains hidden, even after centuries of observation. The galaxy grows in the data, and with every increase it demands another search through the dark for the material that should already have been found. The correction does not remain local for long. Once the Milky Way grows beyond its older boundary, a more unsettling possibility begins to spread through astronomy. The home galaxy may not be the exception. It may be the warning. If one large spiral is measured too narrowly because observers focus on its brightest stars, its most obvious disk, and the easiest part of its structure to photograph, then the same mistake may already be woven into the wider map of the universe. The thought is difficult to ignore because the method itself seems vulnerable. For much of modern astronomy, galaxies are classified and compared by the part that shines most clearly. The bright disk, the visible bulge, the luminous star-forming arms, the central bar when one is present, these become the features from which size, type, and evolutionary stage are often inferred. But if the Milky Way teaches anything, it is that the visible body can be only the inner declaration of something much larger. The dim outskirts, the stellar halo, the streams of consumed dwarfs, the circumgalactic gas, and the dark matter envelope may extend far beyond the familiar image. Once that lesson is learned at home, it becomes hard not to carry it outward. And when it is carried outward, the cosmic census begins to look provisional in a new way. Astronomy has always depended on incomplete light. A distant galaxy is easier to see as a whole than the Milky Way, but not easier to see completely. The farther away a galaxy lies, the more its faint outskirts dissolve into background noise. Surface brightness dims with distance. Dust obscures internal structure. Observing time is limited. Instruments have thresholds. Astronomers can trace the bright center quickly, but the ghostly outer regions demand deeper exposures, cleaner subtraction of background light, wider fields of view, and more patience than surveys can always afford. This means the same bias that once shaped the old Milky Way map may exist elsewhere in a quieter form. A galaxy may be catalogued by the part that announces itself, while the part that whispers is left undercounted. The result is not necessarily a dramatic doubling in every case. Some galaxies may be only modestly larger than their older measurements suggest. Others may be much broader, when their faint stellar envelopes and dark matter domains are taken seriously. But the common pattern matters more than the exact factor. The universe may be full of systems whose real extent is concealed by the fact that their brightest regions are the easiest to trust. This suspicion is strengthened by deeper imaging. Over the past decades, large surveys and dedicated observations have increasingly revealed that many galaxies possess low surface brightness outskirts, tidal streams, shells, diffuse halos, and extended disks that older catalogues either miss or compress into the background. The Sloan Digital Sky Survey changes the field by mapping large areas of sky with unprecedented detail and consistency. Hubble reveals fine structure in distant systems. Ground-based telescopes with long exposures uncover faint outer arms and debris. James Webb, though designed above all to reach the early universe in infrared light, adds new sensitivity to dim and dusty environments, and reinforces the broader lesson that galaxies are often more structured, more layered, and more extended than simple visible classification suggest. What emerges is not a single revolutionary number, but a change in attitude. The visible edge stops looking trustworthy by itself. In nearby galaxies, the evidence becomes especially difficult to dismiss. Andromeda is the clearest example because it is close enough for detailed mapping and large enough to be compared directly with the Milky Way. For years it is presented as a majestic spiral somewhat broader than the traditional Milky Way, yet still comfortably bounded in the imagination. Then deeper surveys revealed giant stellar streams, outer disk distortions, faint populations of stars extending far from the bright structure, and a surrounding environment full of disrupted satellites and halo complexity. Andromeda begins to resemble a system that has also been judged too much by its brightest body. Its visible form remains elegant, but its actual sphere of influence and its layered outskirts are harder to contain in a single simple diameter. The same is true, though on smaller scales, for Triangulum and for many other spirals studied in increasing depth. What first appears as a neat disk often turns out to be accompanied by faint extended components, warped gas layers, peripheral star formation, and evidence of past mergers. In other words, the galaxy is often larger than the standard picture allows, not because astronomers are careless, but because the universe rewards deeper looking with larger structures. This has consequences far beyond the naming of diameters. Galaxies are not measured merely for the pleasure of measurement. Their sizes feed into mass estimates, interaction histories, satellite counts, merger rates, and models of how cosmic structure grows over time. If spirals in general are larger and heavier than older catalogues imply, then galaxy groups become denser with overlapping influence. Encounters become more common. Tidal interactions begin sooner. The space between galaxies becomes less empty in a dynamical sense. The local group no longer looks exceptional in this regard. It may simply be a nearby example of a general truth. Large galaxies do not sit as isolated islands in black nothingness. They occupy broad gravitational territories with fading edges, diffuse gas, stellar debris, and invisible halos that extend into regions once treated as unclaimed. That shift matters for cosmology, because cosmology often turns galaxies into units. It counts them, groups them, weighs them, and uses them to trace the large-scale web of matter across the universe. But a unit that is systematically underestimated is a dangerous unit. If a great many galaxies have been measured mainly by their luminous centers, then the inferred density of cosmic structure may need revision. Cluster dynamics may need refinement. The rates at which galaxies merge and exchange matter may be somewhat different from older assumptions. Even the interpretation of the early universe may begin to wobble, because astronomers compare young galaxies to mature ones partly through structural expectations that depend on what a galaxy is considered to be. A more extended present-day galaxy may imply a more prolonged and layered formation history than the classic bright disk alone suggests. There is also a deeper psychological change buried in this. For much of modern astronomy, progress often seems to come from seeing farther. The next larger telescope reaches more distant galaxies, earlier cosmic epochs, fainter sources at the edge of the observable universe. But the revision now taking shape reminds the field that progress also comes from seeing more completely. A nearby galaxy poorly measured can distort the meaning of a distant one. An outer halo missed in one system can bias the interpretation of many others. The great correction is not only outward, it is downward into the faint levels of structure that sit beneath the thresholds of easier observation. The cosmos becomes more crowded not because new objects suddenly appear from nowhere, but because old objects reveal broader bodies than expected. And once that happens, the universe begins to feel less like a collection of separated shapes and more like a hierarchy of overlapping gradients, spirals, groups, clusters, and superclusters all seem to blur at the edges when enough depth is applied. This invites a more speculative question. If the underestimation of galactic size is widespread, Could some of the universe's tensions partly arise from the fact that astronomers have been comparing incomplete structures, dark matter distributions, merger histories, star formation efficiency? Even the environmental effects that shape galaxies may all depend on how much of a galaxy is counted in the first place. It would be too much to claim that every major cosmological puzzle reduces to this one issue. The evidence does not support such simplicity, but it is no longer unreasonable to wonder whether some persistent mismatches between models and observations survive because the observational side is still biased toward the bright inner regions of cosmic systems. The faint outskirts may contain not the whole answer, but an important missing piece. This is where the section turns slightly darker in mood. A universal correction is more disturbing than a local one because it threatens trust in the scale of comparison itself. The Milky Way being larger than expected is an embarrassment. Many galaxies being larger than expected is a methodological tremor. It means astronomy may have been measuring a filtered universe, one selected by ease of detection rather than by completeness of structure. The bright parts are real, but they are not the whole. The catalogue remains valuable, but it may be cataloguing inner galaxies inside outer ones. It may be naming the cores while only dimly recognizing the full estates around them. That possibility does not erase the achievements of modern observation. It reframes them. It suggests that every galaxy image may contain an unspoken warning at its edge, where the visible light fades into uncertainty. The edge may not be the end. It may only be the point where the instruments, the exposure, the sky background, and human confidence stop together. Beyond that point, the galaxy may still continue in stars too faint to matter at first glance, in gas too diffuse to draw a clean shape, in tidal remnants of vanished companions, and in dark matter that gives the entire structure its true scale without ever appearing in the image itself. The Milky Way teaches this first because it is home. But once the lesson is learned, it becomes harder to look at any spiral without suspecting that the known galaxy is only the bright confession of a larger hidden form, and that the universe as a whole may already be wider, denser, and more entangled than the old luminous map has yet admitted. The story reaches its most delicate point when James Webb turns away from the Milky Way and looks outward so far that distance becomes time. This is where the earlier correction begins to echo in a different register. At home, the lesson is that a galaxy can be larger, older in structure, and more layered than its bright image suggests, far away. Webb begins finding hints that the young universe may also be more developed, more crowded, and more organized than many models expect at such early times. The telescope is designed for precisely this frontier. By observing in infrared light, Webb can detect radiation stretched by cosmic expansion from the earliest luminous structures into longer wavelengths. It sees ancient galaxies not as they are now, but as they appear when the universe itself is still in youth. In principle, this should allow astronomy to watch the first chapters of galaxy formation unfold in sequence. The expectation is not total darkness, but relative simplicity. The earliest galaxies should be small, clumpy, chemically primitive, and still assembling. Their stars should be young, their structure should be rough, their black holes should be growing, but not yet dominant on the scale later epochs reveal. Then Webb begins returning images and data that are at once thrilling and slightly disobedient. Some early galaxies appear brighter than expected. Some seem more massive than expected. Some show signs of dust, structure, or apparent maturity arriving suspiciously soon after the beginning of cosmic star formation. The farther astronomy looks back, the more it expects to see childhood. In several cases, Webb seems to glimpse adolescence already underway. This is not a settled revolution. It is important that the uncertainty remains visible. Some of the earliest reported objects are later revised when better spectroscopy replaces initial estimates. Some turn out to be closer than first thought. Some may be affected by dust, lensing, active galactic nuclei, or biases in how brightness is translated into mass. Astronomers know this and respond the way science usually responds when an instrument suddenly opens a new window. They test, recalibrate, compare, argue, and sort the robust from the premature. Yet even after caution does its work, the general unease does not vanish. Webb still reveals a young universe that often appears unexpectedly efficient at building large, luminous structures. The problem is not that the standard cosmological model immediately fails. The problem is that some observations press against its more comfortable intuitions. Galaxies seem to gather stars quickly. Some central black holes appear to gain enormous mass very early. Heavy elements and dust, which require earlier generations of stars to forge them, sometimes appear sooner than many expectations prefer. The young cosmos looks busy. It looks like it has been working before the moment at which observers thought the main work should have been able to begin. This is where the memory of the Milky Way becomes relevant again, at home. Astronomers discover that they may have mistaken the bright inner region for the whole system. In the early universe, a different version of the same caution appears. Perhaps the first bright galaxies are not impossible. Perhaps older theories are simply underestimating how quickly structure can emerge under the right conditions. Perhaps star formation in dense primordial environments is more efficient than expected. Perhaps the first stars are unusually massive. Perhaps black holes seed themselves more effectively than current models assume. All of these possibilities remain on the table. But beneath them lies a sharper question. What if the observations do not merely ask for faster formation inside the existing timeline? What if they suggest that the timeline itself hides a prehistory that is the edge where the title's deeper promise begins to stir? Webb does not photograph a time before the Big Bang. No telescope does. The Big Bang is not an explosion inside space that leaves a visible surface behind it in the ordinary sense. It is the hot early state of the expanding universe itself, the point beyond which current physics loses confidence. The earliest direct light that can be seen from the young cosmos comes not from the instant of the Big Bang, but from the cosmic microwave background, released when the universe cools enough for light to travel freely. Before that, the plasma is opaque. Before that, theory takes over. This means any claim that Webb has detected something older than the Big Bang must be treated with great care. It has not seen through the beginning like a camera peering past a curtain. What it has done, more subtly, and perhaps more disturbingly, is reveal structures whose existence may be easier to explain if the visible beginning is not the whole beginning. That is not the same claim, but it is the claim that matters. Some cosmologists respond to the Webb tension conservatively. They adjust star formation recipes, revisit feedback models, test different assumptions about dust, and refine how early galaxy masses are inferred from brightness. This is the normal path of science, and it may yet account for much of the tension. But speculative frameworks wait nearby because the anomalies touch a familiar fault line in cosmology. The Big Bang has long been understood not as a fully explained origin, but as the earliest well-described phase of the present universe. General relativity can run the cosmic movie backward only so far before densities and temperatures climb into a regime where the mathematics breaks down. The singularity often spoken of in popular accounts is less a confirmed physical object than a sign that the theory has reached its limit. That leaves a conceptual opening. There may be nothing before. There may be something before that current physics cannot yet describe. There may be a bounce from an earlier contracting universe. There may be a cyclic sequence of cosmic phases. There may be a quantum prehistory in which ordinary space-time, as humans understand it, has not yet emerged. These are not discoveries. They are possibilities. and for decades they remain largely in the province of theory, because observations do not clearly force the issue. Webb changes that mood, not by proving any of them, but by making the old simplicity harder to rest in. The unease grows through accumulation. Galaxies appear too bright too soon. Structures look too settled too early. Black holes seem too massive after too little time. Dust implies previous stellar generations with suspicious haste. None of these facts alone proves a universe before the universe, but together they create the atmosphere in which such ideas stop feeling like purely abstract indulgence and begin to feel like one class of responses among several. The most careful thinkers resist dramatic claims. They note that cosmology has seen tensions before. They point out that early measurements often overshoot and later converge. They remind the field that selection effects can exaggerate the presence of unusually bright early galaxies because the brightest examples are easiest to detect first. This is all true, and it matters. But the mystery remains interesting precisely because caution does not erase it. Even revised downward, several early structures still appear unexpectedly mature. The universe is young, and yet some of its inhabitants already look like survivors of a longer history. This is where language becomes dangerous. Older than the Big Bang can mean many things. It can mean literally surviving from a prior cosmic cycle. It can mean seeded by conditions inherited from a pre-Big Bang quantum state. It can mean explained more naturally by a cosmology in which the hot beginning is a transition rather than an absolute start. Or, in a more modest sense, it can simply mean that the visible evidence forces astronomers to treat the beginning as less complete and less self-contained than older, simplified stories imply. Webb stands closest to that modest but profound version. It does not show an earlier universe directly. It shows a young universe acting as though it may have deeper roots than current narrative habits comfortably describe. The telescope's power makes this especially unsettling, because it is not finding one outrageous object and nothing else. It is finding a pattern of premature competence. The early cosmos does not always look blankly primitive. In some fields it looks active, layered, and unnervingly efficient. That is the phrase that lingers, unnervingly efficient. A universe only beginning its visible career should not, by older intuition, be so quick to produce luminous galaxies, structured systems, and gigantic black holes. Yet there they are, or enough of them are there to keep the question alive. What if the first visible chapter is already late in the story? What if the cosmos, like the Milky Way, has been judged too much by the brightest layer available to ordinary observation? What if the beginning humans have learned to call the beginning as only the first surface that becomes readable, while the deeper architecture lies hidden behind it? That question remains speculative. It should remain speculative. But Webb has done enough to make it difficult to ignore. The telescope does not yet announce what comes before the Big Bang. It does something more subtle and perhaps more powerful. It looks into the young universe and finds traces of behaviour that seem to belong to something older than youth should permit. The final shift in the story is not a claim of proof. It is a change in what feels permissible to ask, for most of modern cosmology. The Big Bang functions as a practical beginning. It is the earliest hot, dense state that present theory can describe with confidence, the point beyond which the known equations no longer give a stable picture that can be trusted without qualification. This distinction matters. The Big Bang is often spoken of as if it were the absolute origin of everything, but in working science it is more carefully understood as the earliest reliably modelled chapter of the present expanding universe. Before that chapter, certainty fails. Space and time as normally described may not yet behave in familiar ways. Matter and energy may not fit the later categories. Gravity itself may require a quantum treatment not yet fully achieved. This means the line called beginning has always been less solid than popular language suggests. It marks the edge of reliable description, not necessarily the edge of all reality. For decades, that opening remains mostly theoretical because observation does not press hard enough on it. Then the universe starts looking older than its visible youth should allow. That is where the title begins to earn its deeper meaning. James Webb does not image a universe before the Big Bang. It does something more unsettling. It reveals early structures whose maturity seems out of proportion to the time available under the simplest expectations. The result is not a photographic glimpse of a previous cosmos. It is a pressure on interpretation. If galaxies, stars, dust, and black holes appear to organize themselves very quickly after the hot beginning, then either the universe is better at building structure than older models suggest, or the visible beginning is sitting on top of a deeper preparation phase not yet understood. That second idea is the dangerous one, because once it enters the room, the Big Bang stops behaving like a wall and starts behaving like a horizon. A horizon hides what lies beyond it, not because nothing is there, but because the observer cannot yet see past it. The analogy is imperfect, yet it captures the emotional change. The beginning ceases to feel like an absolute point and starts to feel like the first luminous surface of a longer process. Cosmology already contains possible versions of such a process. There are bounce models in which a prior contracting universe compresses and then rebounds into expansion. There are cyclic models in which cosmic phases repeat on timescales too large for ordinary imagination. There are proposals in which the Big Bang emerges from quantum conditions where space and time as later known do not yet exist in their ordinary form. There are inflationary ideas that sometimes imply a wider landscape of expanding regions, with the observable universe only one local expression of a much larger process. None of these frameworks has one final authority. Each has difficulties. Each depends on physics not yet complete. Yet Webb's early findings make them feel less like distant philosophical curiosities and more like serious shelters into which explanation might move if the pressure from observation keeps building. The strange beauty of the moment lies in how indirect it is. Nothing ancient steps out and declares a previous universe. Nothing unmistakable appears with a label that says older than the Big Bang. Instead, the cosmos behaves with suspicious competence. It forms luminous galaxies quickly. It grows large black holes quickly. It seems to enrich itself with heavy elements and dust on timescales that strain older intuitions. The simplest response is that the universe is merely more efficient than expected. That may yet be true, but efficiency itself can become a clue. Efficient compared to what? Efficient because of what hidden conditions? Efficient because the earliest visible structures inherit advantages from a prior state. Once the question is asked in that form, the story changes from one of premature galaxies to one of concealed preparation. This is where the Milky Way's correction returns one last time as more than an analogy. At home, astronomers realize that the bright visible galaxy is not the whole galaxy. The true structure includes faint outskirts, hidden populations, streams of destroyed companions, surrounding gas, and an invisible halo that dominates the total mass. The visible part is real, but incomplete. Far away in time, Webb may be teaching the same lesson on a larger stage. The earliest visible universe may be real, but incomplete. The hot beginning may be the luminous inner region of a deeper cosmological structure, just as the spiral disk is the luminous inner region of a deeper galactic one. In both cases, the first visible layer invites premature certainty. In both cases, improved observation weakens that certainty and widens the hidden domain beyond it. If that pattern holds, then the most dangerous mistake in cosmology may not be getting a number slightly wrong. It may be mistaking the first readable surface for the true beginning of the thing itself. There are other hints, though none decisive. The cosmic microwave background, that ancient light released when the young universe becomes transparent, is remarkably smooth, yet not perfectly so. Tiny fluctuations in it seed the later growth of galaxies. Some researchers have long wondered whether subtle anomalies in that background, cold spots, alignments, statistical oddities, might hint at prehistory, or at least at processes not captured by the most minimal models. Most of these anomalies remain controversial. Some may be chance, some may be artifacts of data handling, some may eventually disappear into better understanding. But the atmosphere they create matters because Webb's findings do not arrive in a vacuum. They join a cosmology already aware that its beginning, though impressively modelled, is not fully explained. The early universe has always carried unanswered questions about inflation, singularities, entropy, and the origin of the conditions from which the later cosmos unfolds. Webb does not invent those questions, it sharpens their tone. Another possibility stays quieter but equally intriguing. Perhaps what looks older than the Big Bang is not older in time, but older in structure. In other words, perhaps the early universe develops complexity so rapidly that it mimics inheritance. A galaxy appears mature not because it is literally left over from a previous cosmos, but because the laws of formation in the first few 100 million years are capable of producing maturity at speeds not yet properly respected. This possibility is less dramatic, but it does not diminish the mystery. It still means that the universe's first visible era contains powers of self-organization stronger than the narrative of gradual assembly once preferred. It still means the cosmos is stranger at birth than expected, and in a subtle way it leads to a similar philosophical discomfort, whether the deeper cause is a prior phase or a hidden efficiency within the visible phase. The human story of beginnings becomes less secure. The early universe stops feeling like a simple nursery and begins to resemble a place where important work is already well underway before the observer expects it. James Webb therefore changes the question more than the answer. The older question asks what the first galaxies look like. The new question asks why they look as though they have been given more time than time seems to allow. That question reaches backward toward the beginning itself. It invites caution, because the history of astronomy is full of anomalies later absorbed into better ordinary explanations. But it also invites honesty. There are moments when the ordinary explanation is not yet in hand, and this is one of them. The telescope has not broken the Big Bang. It has made the boundary around it feel less settled. It has turned the beginning from a firm starting line into a region of growing interpretive pressure. Perhaps future models of star formation, dark matter behavior, black hole seeding, and early feedback will absorb the tension and restore calm. Perhaps they will not. Perhaps the pressure will instead widen until cosmology accepts that the hot beginning is not the first act, only the first visible one. If that happens, the phrase older than the Big Bang will still need care. It will not mean that Webb has photographed before time in a simple literal sense. It will mean that observation has begun to expose signs of depth beneath the oldest layer humans can currently see. A structure behind the surface, a preparation behind the appearance, a prehistory behind the first light. That possibility is enough to leave the story open, which is where it belongs. The Milky Way grows larger when astronomy learns to distrust the visible edge. The early universe grows stranger when Webb learns to distrust the visible beginning. In both cases, the same quiet lesson returns. The cosmos may not start where it first becomes easy to see.